This video is about glycolysis, and this is a very quick review, so let's get right into it. So from glucose, we have glucose 6-phosphate, and the enzyme we are using is either hexokinase or glucokinase. Glucokinase in the liver because it says gluco, there's an L there, and hexokinase is everywhere else. Glucokinase has very high Km but low affinity, but hexokinase has low Km and high affinity. What does that really mean? It means that you need lots of sugar to stimulate the glucokinase that is in the liver. That's why it has high Km. But you don't need that much sugar in the other tissues where we are using hexokinase to do glycolysis or to start the process of glycolysis. From glucose to glucose 6-phosphate, we're using one molecule of ATP, turning ATP to ADP. We're also using magnesium as the ion. Okay, so that's the first step. Moving on to the next step. Glucose 6-phosphate to fructose 6-phosphate is achieved by the enzyme isomerase. Glucose 6-phosphate and fructose 6-phosphate are isomers of each other. Therefore, they are in equilibrium, so they can go back and forth. This is just shuffling the hydroxyl group from one position to the other. Now we have fructose 6-phosphate being converted to fructose 1,6-bisphosphate. And this enzyme, the enzyme that is required here is PFK1. Now, fructose 6-phosphate can either go to form fructose 1,6-bisphosphate or it can also form fructose 2,6-bisphosphate. And this enzyme is going to be PFK2. Fructose 6-phosphate getting converted to fructose 1,6-bisphosphate uses 1 ATP converting to ADP. So 1 ATP is being converted to ADP, and the same thing is happening here. It's also using 1 ATP being converted to ADP. This PFK1 is also the rate-limiting enzyme. What is a rate-limiting enzyme? It means it has the slowest step. When we draw a rate-limiting enzyme, we're supposed to get a sigmoidal curve. That's what happens. Whenever we draw a rate-limiting enzyme, it always ends up being a sigmoidal curve. And this is also the slowest step in the entire glycolytic pathway. Now, the formation of fructose 2,6-bisphosphate, the reason it happens is because when there is so much sugar trickling down the system, the system gets, or the glycolytic pathway gets overloaded. So it kind of holds off as fructose 2,6-bisphosphate before it can channel all its products to fructose 1,6-bisphosphate. When there's a significant amount of increase in fructose 2,6-bisphosphate, when it increases significantly, this has an allosteric effect on this pathway. So it stimulates this PFK1, making more and more fructose 1,6-bisphosphate. The enzymes that stimulates PFK2 is going to be insulin, and the one that inhibits is going to be glucagon. Don't get confused with the fact that PFK1 is stimulated by insulin or inhibited by glucagon. No, it's only going to be PFK2 which is going to be stimulated by insulin, inhibited by glucagon. So those were the regulators for PFK2. For PFK1, the regulators are citrate, which is going to have a negative effect on PFK1, ATP, which is going to have a negative effect on PFK1, AMP is going to have a positive effect on PFK1, and fructose 2,6-bisphosphate, so this product right here is going to also have a positive effect, and this was allosteric effect on PFK1. So those were the regulators for PFK1. Now moving on to the next page, from fructose 1,6-bisphosphate, we're going to use an enzyme aldolase, which is going to give us 2 molecules of 3 carbons. So fructose 1,6-bisphosphate had 6 carbons, glyceraldehyde 3-phosphate has 3 carbons, dihydroxyacetone phosphate has 3 carbons. So the 6 carbon split into 3 and 3, making glyceraldehyde 3-phosphate and DHAP. And this is achieved by the enzyme aldolase. Glyceraldehyde 3-phosphate are isomers of DHAP, so they do interchange among each other constantly. And this isomerization is achieved by the enzyme isomerase. Just like glucose 6-phosphate to fructose 6-phosphate, we used isomerase. Now from glyceraldehyde 3-phosphate, we are getting 1,3-bisphosphoglycerate. And the enzyme we are using here is glyceraldehyde 3-phosphodehydrogenase. We're removing one of the hydrogen, and that hydrogen is converting NAD to NADH. Now this process also requires one inorganic phosphate and uses mercury as one of the metabolites. Now from 1,3-bisphosphoglycerate, we are making 3-phosphoglycerate using the enzyme phosphoglycerate kinase. this process is also making 1 ATP from 1 ADP. But do remember that there is two of these going on, because these are one of the 3 carbon atoms, right? There is another one, so really we're making 2 ATPs than 1 ATP. Now 1,3-BPG in red blood cells can be converted to 2,3-BPG, and you know that 2,3-BPG has greater affinity for oxygen when the hemoglobin has greater affinity for hemoglobin when it is in deoxygenated state than in oxygenated state. So there is also that step going on right here. But moving on, from 3-phosphoglycerate to 2-phosphoglycerate, that step is achieved by mutase. And from 2-phosphoglycerate to PEP, or phosphainositol pyruvate, is achieved by enolase. Is also inhibited by fluoride, which is found in a lot of paste. A lot of elderly people get fluoride poisoning, so they have vision of the enzyme enolase. So from PEP to pyruvate, this is achieved by the enzyme pyruvate kinase, which also makes another ATP from ADP. Again, I want to mention that this is 2 of these steps are going on simultaneously, so really we're making 2 ATP rather than 1 ATP. Now pyruvate kinase is inhibited by ATP, acetyl-CoA, alanine, and glucagon, and it's stimulated by fructose 1,6-bisphosphate, which is right here. It's stimulated by fructose 1,6-bisphosphate all the way to here, and it's also stimulated by insulin. So that was my quick review of glycolysis. That was under 7 minutes, so I think I did a good job. Hope you liked it. See you in my next video.